Welcome to lecture 4, the final lecture in our kinetics series. So in this lecture you will be able to describe how reaction rates change with temperature and use kinetics equations to do accelerated stability testing and determine shelf life of medicines. So the concepts here will be that relationship between temperature and rates and drug stability testing, and there'll be maths that you'll be using while doing the drug stability testing that will involve the Arrhenius equation, which is going to be introduced to you, and combining Arrhenius with rate equations that you've already learned to calculate product stability. So experience tells us that the rates of a chemical reaction will increase with temperature. Now we know so far from the rate law that the rate of a reaction does depend on the concentration of reactants that are a part of the rate determining step of the mechanism, and also multiplied by the rate constant. So that would mean, since the concentration itself isn't dependent on temperature, that it is the rate constant that will change with temperature. And from experience, we've seen that a 10-degree increase in temperature leads to doubling the rate. So if you do an experiment at room temperature, it's likely to be roughly 4 times the rate that it might be if you did that same experiment in the fridge. While we move forward, expect another logarithmic relationship, because if we look at the rate constant against temperature, we will see an increase like this, and you can see that this is increasing exponentially. So the rate constant is increasing exponentially as you increase temperature. So, as we've said, experience tells us that rates of chemical reactions increase with temperature. We know that we're going to be able to dissolve something in water, for example, if we heat it up. But why is this? Now, one way of helping us to think about rates of reactions is to consider collision theory. So collision theory considers a chemical reaction to occur as a result of molecular collisions. So the likelihood that the reactant molecules will collide, thus leading to the possibility of reaction. So there you would say that the rate of reaction will be proportional to the number of collisions per second. Reactions require energy though. So once they have collided, the two colliding molecules need to have enough energy to actually break bonds and form bonds. And the energy provided is by the kinetic energy of the colliding molecules. And the kinetic energy will then be converted to potential energy on collision. And if there's enough energy to break and form new bonds, then we will be able to see a reaction as a result of that collision. So collision theory will say, first of all, you need there to be collisions, and then we need those collisions, those interactions between molecules, to have enough energy to allow for reaction to occur. So that means that not all collisions lead to reaction. For reaction to occur, the kinetic energy of the colliding molecules, according to collision theory, needs to be greater than or equal to the activation energy. And if you think about that diagram that we saw at the end of the last lecture, looking at activation energy required to go between reactants and intermediate, and then the intermediate state and the product state of that two-step reaction that we were looking at. Then you can see that the activation energy will determine if reaction will occur It will determine if we can get to that transition state. That means that the activation energy is a barrier to reaction. Okay? And it's the minimum energy required for reaction. So if we increase the rate, which means the rate constant, with temperature, we can now see an explanation for why that would be. Okay, so the rate constant will be dependent on this activation energy. Arrhenius showed in 1889 that many reactions could be described with rate constants in the following form. So he noticed that the rate constant will equal to A, which is a pre-exponential factor, so a constant, times the e to the power of EA, which is our activation energy, divided by R, the gas constant, times the temperature. So this means as you increase the temperature, you see that the reaction will go faster. Okay, they will have less of a impact on the activation energy. So let's look at this equation for rate constant and see if we can understand what each of the parameters within that equation mean. First of all, we know the activation energy, EA, is the minimum kinetic energy that the reactants must have in order to form products. Now, the exponential factor contains the activation energy in its term, and the exponential factor is the e to the minus EA over RT part of the equation. That's the exponential part of that equation. And what that gives you is a fraction. So a number that will be less than 1, and it gives you the fraction of collisions with a kinetic energy in excess of the activation energy. We also have A, and A is our pre-exponential factor, and it'll be a measure of the rate at which collisions occur, irrespective of the energy. So you can think of A as how fast collisions occur, the total number of collisions linked to the total number of collisions, and then the exponential factor will account for how many of those, the proportion of those collisions that actually have enough energy for reaction to occur. That means the overall expression A e to the minus EA over RT, and E is the exponent, exponential is EXP. Some people use EXP instead of the little e there. So that term, A times E to the minus EA over RT, actually tells us the rate of successful collisions. Okay, so that is one way to interpret the meaning of Arrhenius equation. Now, if we look at Arrhenius equation, it gives you, as you know, an exponential increase in rate constant against temperature. And what you can do is you can manipulate that equation to make it so you can use it to work out some of those constants. If you log both sides, natural log both sides of the equation, you're going to be able to remove that exponent on the right side of the equation. Okay, so that would lead to natural log of K, and then you would split the two parts on the other side, so to equal natural log A, and then if you natural log e to the minus EA over RT, you remove the e. So you'd have to go back to your maths to be able to understand that, and it would lead to just minus EA over RT. So the reason we've natural logged both sides of this equation is to remove that exponent term. Okay, so we would end up with natural log K equals natural log A minus EA over RT. Now, if I just rearrange that a little bit to put it in a slightly different format, so I'm going to move the minus EA over RT and put it in front of the log of A just to give it a slightly different appearance, you can see that this can be linked to a y equals mx plus c equation. So the two variables here are the rate constant, which changes with temperature. The other terms are constant. So that means that if we plot natural log of k against 1 over temperature, we will get a straight line where the gradient of that line, which is m, will be minus EA over RT. So since the gradient is negative, you know that this will be a straight line that goes down as you move from left to right. And the place where it crosses the y-axis will give you log of A, natural log of A. Okay, so let's plot that there. So you can see that if you plot natural log of K against 1 over T, and these numbers mean, just to make the numbers easier, they've multiplied that by 1,000, but don't worry about that multiplied by 1,000 on the x-axis there. So it's natural log of K over 1 over T against 1 over T. And you'll see that that's a straight line. And we can get the activation energy from the gradient of that line. It's the activation energy, because the gradient equals minus EA over R, where R is the gas constant. Okay, so that allows us to work out the activation energy. So a plot of log of K versus 1 over T, we can get from the gradient the activation energy. So the Arrhenius equation is useful. It allows us to understand the impact of temperature on the rate of the reaction, and it allows us to think about rate of reaction in terms of collisions, and links that to collision theory. But it also, in this form, with the log form, allows us to plot a straight line that can give us the activation energy. Now, you don't have to plot data like that where you have done multiple experiments. Here, say 5 experiments have been carried out at 5 different temperatures, and the rate constant has been determined at each temperature in order for this equation, this graph to be formed. You can calculate EA without plotting that graph by just doing 2 experiments at 2 different concentrations. Okay, so you've got temperature 1, not concentration, sorry, temperatures. You've got temperature 1, and you've worked out the rate constant at that temperature, and then you have temperature 2, and you've worked out the rate constant at that temperature. And you're going to notice here similarities when we were looking at Van 't Hoff equation in when we were doing thermodynamics, and there is a huge similarity here that you're going to see as we move forward. Okay, so in this exercise, substitute into the equation the values of the rate of the temperature 1 and K1 into 2 equations. Okay, and then using a concept that I'm just going to show you how this is done here, where you then have K1 of one equation with K1, which is our rate constant 1, and temperature 1, and K2 for the second experiment, and temperature 2. So we have 2 equations, and if you take those 2 equations away from each other, so K1 minus log of K1 minus natural log of K2, and then you equal the right hand of the top equation minus the right hand of the bottom of the equation and rearrange it, you will get this equation here. And that can be simplified further, because log of K1 minus log of K2 equals natural log of K1 over K2. And it will equal EA over R, and then in brackets 1 over temperature 2 minus 1 over temperature 1. Now, there are a few steps that I have missed there. You do not need to remember the maths, because remember, if I need you to be able to discuss these equations in an exam, I will give them to you. But the maths here is very, very similar to the detailed maths that I provided for people who wanted to see it for determining the Van 't Hoff equation. So you can look back at that. But remember, here is rate constant. They do start with different equations, but the concept in terms of the maths is very similar. So this is still the Arrhenius equation. So we've now got three different forms of the same equation, really. Okay, the basis of all of these equations is the Arrhenius equation. This form of the Arrhenius equation allows you to work out the activation energy from only two experiments, K1 and K2. So you have two experiments at two different temperatures, and you can work out the activation energy. So for the numbers that we had on the previous slides, if you were to try to plug them into this equation, and I suggest you try to do that yourselves to see if you can get the answer, then you will end up with the details that I'm going to show underneath in a moment. You can pause now to try that if you would like. So if you substitute those values into the equation, then you will get an activation energy that equals 1.85 times 10 to the 3 joules per mole for the activation energy. Now the temperature has to be in Kelvin, and you need to make sure your gas constant is in joules per Kelvin per mole. And in this case, well, we have also our units of K, but remember they'll be cancelled because we have logged that term. But just to remind you what the units are for each of the components that were in that equation.